So in the last few videos, we looked at vapor pressure of liquid solutions, and then we said that vapor pressure of any liquid is going to be lower when it is a part of a solution than it is in its pure form. So in the next few videos, we'll talk about a few other physical properties of liquid solutions that differ considerably from those of pure substances. For example, changes in boiling point, changes in freezing point, osmotic pressure of solutions. So all these properties are in fact called colligative properties, and by definition, these properties depend primarily on the number of solute particles regardless of the kind of particles. Now we know that for vapor pressure, the kind of particles obviously matters. We did this whole section on Raoult's law, deviations from Raoult's law, and we said how type of components and the interactions, intermolecular interactions matter. But for the first approximation, the primary dependence is on the number of particles or the concentration of the solute in a particular solvent. So let's now look at what happens to properties like boiling point, for example, of liquids, when they are part of a solution versus when they are in their pure form. So let's think about what we already know about boiling points. So boiling point, so first of all, we know that the vapor pressure of any liquid actually goes up with temperature. So that's pretty much the only thing vapor pressure of a liquid depends on. Vapor pressure of a liquid increases with increase in temperature. So if you were to draw a graph with vapor pressure, and temperature, let's say this is in Kelvin, so you'll see something like this. Now the reason I'm stopping this curve here and not taking it further is, let's say this were just water or any liquid. It has a certain freezing temperature, so below which it's not a liquid. So I just start the curve from, let's say, a temperature from where this particular material exists in liquid phase. So in any case, and we also know that boiling point, by definition, it is the temperature at which the vapor pressure of liquid is equal to the atmospheric pressure. So temperature at which vapor pressure of the liquid equals the atmospheric pressure. So for example, for pure water at 1 atmospheric pressure, pure water at 1 atm pressure boils at 100 C or 373.15 Kelvin. So if this were the atmospheric pressure, 1 atm, then the temperature at which that vapor pressure equals the 1 atmospheric pressure is going to be TB0, that is the boiling point of water or whatever liquid you're looking at in its pure form. So we also know that if you were to take this water and dissolve a non-volatile solute, like for example table sugar or common salt in it, then vapor pressure of this water in the solution form, pressure of water in solution, is going to be lower than vapor pressure of pure water at any given temperature. So if you were to mark the vapor pressure of the solution, or water in solution, on this graph, then it will look something like this. So in this dotted line. So it will actually closely follow the other curve, but it will be lower. At every given temperature, you have a lower vapor pressure. So now based on all this information, what can we say about the boiling point of this solution? So the solution is going to have a higher boiling point. So let's just erase this and write it differently here. So this will be a TB0, the boiling point of pure liquid, and then this will be TB of this liquid in the solution. So So that means that for the vapor pressure to catch up and become equal to the atmospheric pressure, in this case it's 1 atmosphere, it has to actually go to a higher temperature. So that's why there is an increase in the boiling point of the solution. And the difference here, the difference or the magnitude of increase in this boiling point, that is the elevation in the boiling point, and that is represented as delta TB. So this delta TB, as you can imagine, the magnitude of increase in boiling point is going to be directly related to the magnitude of decrease in vapor pressure. And as we already discussed earlier, and the whole section of Raoult's law, the decrease in vapor pressure is directly proportional to the concentration of the solute in the solution. So as a result, you can say that delta TB is going to be proportional to the solute concentration. So the relationship between the magnitude of increase in boiling point and the concentration can actually be expressed as delta TB equals m times Kb, where m is the solute concentration expressed as molality, this is for the solute, and Kb is obviously the proportionality constant, and it's called the molal boiling point elevation constant, nothing creative there. And this is for the solvent. So now you might ask, why is the concentration of solute here expressed as molality and not molarity or mole fraction, for example? So, we've used molarity earlier in our entire discussion of Raoult's law. So why shift to molality here all of a sudden? So the reason being, temperature is a factor here, and density of the solution actually changes, with temperature. And we cannot ignore this effect. So when the density changes for the same mass of the components of the solution, your volume is going to change. So a concentration expressed in molarity is not going to be constant across the entire range of temperatures. So molarity changes, but the molality doesn't change. But molality does not change. So that is one reason why we want to go with molality, because here you just have moles per kg or moles per unit mass of solvent. So those values are not going to change with temperature. Since boiling point here depends on solute concentration, by definition the system is not going to be maintained at a constant concentration if you were to use molarity. So you'll get erroneous values when you're calculating this delta TB here. But if you used molality, you will not encounter this problem. So secondly, one could have used mole fraction, right? And both molality and mole fraction are in fact proportional for relatively dilute solutions. But what happens is molality has a larger numerical value because you're just calculating number of moles per 1 kg of the solvent. So molality has a larger numerical value. But mole fraction, looking at relatively dilute solutions, mole fraction can only take values from 0 to 1. So you might end up with a lot of zeros. So molality allows us to eliminate all the non-significant zeros. Allows to eliminate non-significant zeros. So if you look at the units here, the units here will be for molality, it is moles per kg. So units for Kb will be Kelvin kg per mole. So let's look at a quick example here. So for water, we know the TB0 for water is 100 C, which is 373, to be very precise, 0.15 Kelvin. So let's say we add 1 mole of glucose, 1 mole of glucose to 1 kg of water. For a moment, let's just assume that 1 kg of water can actually dissolve 1 mole of glucose, which is about 180 grams. So this is C6 H12O6. So the elevation and boiling point, to calculate the elevation and boiling point for this solution here, you need to know what the Kb for water is. You don't really care if the water is you dissolving glucose or salt or what other solute, because as we said, for colligative properties, the primary dependence is on the number of particles rather than the kind of particles. But again, keep in mind that there are going to be deviations from it. These are all simple models. So here, Kb for water, it is 0.52 Kelvin kg over mole. So this is given to us. So delta Tb in this case is going to be 0.52 Kelvin. That's all. So it's only about half a degree increase in boiling point. So we'll look at more examples in later videos.